Hey everyone, welcome back. Today, we're tackling a pretty radical question. Can mathematics be deconstructed? I know, it sounds almost absurd. We associate math with absolute certainty, with unshakable truths. But what happens when we apply the tools of Jacques Derrida's deconstruction, a method usually reserved for literature and philosophy, to the seemingly rigid world of mathematics? For those unfamiliar, Derrida was a key figure in post-structuralism. His method of deconstruction is all about taking apart texts, and by texts, he meant anything that conveys meaning, from novels to legal documents to, well, even mathematical equations. Deconstruction isn't about destroying meaning, it's about revealing the hidden assumptions, the internal contradictions, and the underlying power structures embedded within any system of thought. It shows how meaning is never fixed, never absolute, but always dependent on a network of relationships and differences. So, how does this apply to something like the number line? It seems so straightforward, so undeniably true. A continuous line, with numbers extending infinitely in both directions. What could possibly be deconstructed there? Well, let's start by questioning some of the seemingly obvious things. What is a number, anyway? We use them every day, but do we ever really stop to consider their philosophical foundations? There is a whole area of study, the philosophy of mathematics. The number line, for example, relies on the concept of a point. But what is a point? It has no dimension, no size, it's a purely abstract concept. And yet, we build the entire structure of real numbers on this infinitely small, non-existent thing. Or consider the concept of zero. Zero wasn't always accepted as a number. It took centuries for mathematicians to fully incorporate it into their systems. It represented nothingness, which was a philosophically problematic concept for many cultures. Even something as fundamental as addition, 2 plus 2 is equal to 4, relies on certain axioms, basic assumptions that we take to be self-evidently true. But where do these axioms come from? Are they discovered, or are they invented? This is a major debate within the foundations of mathematics. The field of set theory, which attempts to build all of mathematics from the concept of a set, is particularly interesting from a deconstructive perspective. Set theory runs into all sorts of paradoxes, like Russell's paradox, which basically asks, does the set of all sets that do not contain themselves contain itself? It's a logical head-scratcher that highlights the inherent instability of even the most rigorous mathematical systems. Deconstruction would also look at the language we use to describe mathematics. We talk about proving theorems, as if we're uncovering pre-existing truths. But what if the act of proving is itself a form of construction, a way of shaping and defining mathematical reality? Consider the very idea of mathematical logic. We assume that logic is a universal, objective system. But Derrida might argue that even logic itself is a kind of text, a system of rules and conventions that has its own internal biases and limitations. Now, this isn't to say that 2 plus 2 doesn't equal 4, or that mathematics is somehow wrong. Deconstruction isn't about denying the practical usefulness, or the impressive power of mathematical systems. Instead, it's about questioning the absoluteness of mathematical truth. It's about recognizing that even the most seemingly objective systems are built on foundations that are, to some extent, arbitrary, conventional, and perhaps even influenced by social and historical forces. Derrida might argue that the number line, like any other text, is a product of human thought, a way of organizing and understanding the world. It's a powerful tool, no doubt, but it's not a mirror of some pre-existing, independent reality. So, can math be deconstructed? Absolutely. It doesn't mean math is false, but it does mean that the truth of mathematics is more complex, more nuanced, and more human than we often give it credit for. It forces us to confront the inherent limitations of any system of knowledge, even one as seemingly perfect as mathematics. It's a reminder that even the most solid-seeming foundations can be shaken, that questioning assumptions is always a worthwhile endeavor, and that the search for truth is an ongoing and endlessly fascinating process.